Thermodynamics, bunch of definitions. These definitions I will be posting as maybe YouTube shorts and go through each one. Just definition you need to memorize. So enthalpy change of atomization of element. Enthalpy change of 1 mole of gaseous atoms is formed from an element in its standard state. Bond dissociation enthalpy change when all the bonds of the same type and 1 mole of gaseous molecules are broken. Enthalpy change of atomization of a compound. Enthalpy change of 1 mole of a compound in its standard state is converted to gaseous atoms. Whereas enthalpy change of atomization of element, enthalpy change of 1 mole of gaseous atoms is formed from an element in its standard states. Enthalpy change of atomization of a compound, enthalpy change of 1 mole of a compound in its standard state is converted to gaseous atoms. First, electron affinity, enthalpy change of 1 mole of gaseous 1 minus ions is formed from 1 mole of gaseous atoms. Second, electron affinity, enthalpy change of 1 mole of gaseous 2 minus ions is formed from 1 mole of gaseous 1 minus ions. Enthalpy change of hydration, enthalpy change of 1 mole of aqueous ions is formed from 1 mole of gaseous ions. Enthalpy change of 1 mole of aqueous ions is formed from 1 mole of gaseous ions. Enthalpy change of solution, enthalpy change of 1 mole of a solute is dissolved in enough solvent so that no further enthalpy change occurs or further dilution. Lattice enthalpy is a measure of ionic bond strength. Two types of lattice enthalpy. Lattice enthalpy formation, enthalpy change of 1 mole of solid ionic compound is formed from its gaseous ions under standard conditions, and lattice enthalpy of formation is exothermic. Lattice enthalpy of dissociation, enthalpy change of 1 mole of a solid ionic compound is completely dissociated in its gaseous ions under standard conditions. Lattice enthalpy of dissociation is endothermic. Purely ionic model of a lattice assumes that all ions are spherical and they have their charge evenly distributed around them. Positive and negative ions in the lattice aren't exactly spherical. Positive ions polarize neighboring negative ions to different extents. More polarization, more covalent to bonding. You can see here unpolarized ions, positive, negative, pure ionic bonding, polarized ion, positive, that's polarized negative ions, partial covalent bonding. What happens when a solid ionic lattice dissolves in water? The bonds between ions break to give free ions. Bonds between the ions and water are made. So bonds between ions break to give free ions. Bonds between the ions and water are made. Enthalpy change of solutions overall effect on enthalpy of these two things. Bonds between ions break to give free ions. That's endothermic. Bonds between ions and water are made. That's exothermic. Dissolving involves enthalpy change. Water molecules can bond to the ions as oxygen is more electronegative than hydrogen. As oxygen is more electronegative than hydrogen, it draws electrons towards itself, hence creating a dipole. Dipole means that the positively charged hydrogen atoms can bond with form bonds with negative ions. So dipole means that positively charged hydrogen atoms can form bonds with negative ions, and that negatively charged oxygen atoms can form bonds with positive ions. Substances generally only dissolve if the energy released is the same or greater than the energy taken in. Substances generally only dissolve if the energy released is similar or the same or greater than the energy taken in. Therefore, soluble substances tend to have exothermic enthalpies of solution. Enthalpy change of solution can be calculated. Instead of dissolving compound directly, we break the lattice into separate gaseous ions and then we dissolve the gaseous ions in water. So we break the lattice in separate gaseous ions and dissolve the gaseous ions in water. So here's an example, because they really like to ask this one. NaCl solid, R to Na plus aqueous plus Cl minus aqueous, enthalpy change of solution. This is lattice dissociation enthalpy to these single ions with the gaseous ions, and then that's the enthalpy of hydration of sodium, Na plus, and also enthalpy of hydration of Cl minus. It should be separate, right? A classic example they like to use in the exam, around 2 to 3 marks. And remember, enthalpy change of solution definition. Let's go through the definition again. Enthalpy change of solution definition. Enthalpy change of 1 mole of solute is dissolved in enough solvent so that no further enthalpy change occurs or further dilution. So they'll probably ask you in the exam, define this for 2 marks. Define enthalpy of solution, calculate enthalpy change of solution, and you'd have to construct this cycle. Enthalpy change of solution, enthalpy change of 1 mole of solute is dissolved in enough solvent so that no further enthalpy change occurs or further dilution. Entropy S, a measure of the number of ways that particles can be arranged and the number of ways that energy can be shared out between particles. More disordered the particles, higher the entropy. A large positive value, entropy value, shows a high level of disorder. Substances tend towards disorder because they're more energetically stable when there's more disorder. Therefore, particles move to increase entropy. Substances tend towards more disorder More energetically stable ones is more disorder. Particles move to increase entropy. That's why some reactions are feasible, meaning they happen by themselves without the addition of energy. And that's really important to learn. Because you could state what is meant by feasible, but it's just nice to know it for your understanding. So it happens by themselves without addition of energy, even when the reaction is endothermic, delta H positive. S this, meaning standard entropy of substance, entropy of 1 mole of that substance under standard conditions. Entropy of 1 mole of that substance under standard conditions, meaning 100 kilopascals and 25 degrees Celsius or 298 Kelvin. Entropy of 1 mole of that substance under standard conditions. If delta H is negative and delta S is positive, reaction is always feasible at any temperature. And that makes sense because Gibbs free energy change is delta G is equal to delta H minus T delta S. If delta H is negative, I'm doing negative minus a positive value. So minus 10 minus a positive value, which is 10. I'm always going to get a negative value, right? Therefore, because delta G is negative, reaction is going to always be feasible at any temperature. If you flip it around, so delta H is positive and delta S is negative, well then yeah, the opposite is going to happen. Reaction won't be feasible at any temperature because think about delta G is delta H minus T delta S. You're doing a positive minus a negative. But I'm doing a positive minus a negative, which is negative. So those two negatives therefore means it's positive. So therefore delta G is always going to be positive. Reaction won't be feasible at any temperature. If delta H is positive and delta S is positive, reaction won't be feasible at some temperatures, but will be feasible at higher temperatures. If delta H is positive and delta S is negative, and delta S is positive, reaction won't be feasible at some temperatures, but will be at high temperatures. If delta H is negative and delta S is negative, reaction won't be feasible. Reaction will be feasible at low temperatures, but won't be feasible at higher temperatures.